Greetings everyone, welcome back to Calc 1. Time to continue talking about the connection between areas and definite and indefinite integrals. Okay? Or rather just the connection to antiderivatives. That's probably a better way to look at it. You've seen this symbol a couple of lectures ago. We talked about the integral symbol and how it was related to being an antiderivative. Now let's talk about the definite integral instead of the indefinite integral. Okay, and the difference is the definite integral will have values that we call boundaries written beneath and above the integral symbol. And the idea here is that this is going to be equal to what we were just talking about in the last lecture, and that is the actual area between a functional curve and the x-axis. Or a better way of looking at it, instead of just talking about it being an area is one application, but a better way to talk about it is the little twist that I gave on it last time, and that is to think of it as like you're adding up all of the function values. You're adding up all of the y values, which when you have something that's what we call positively signed area like this, and you do this particular summation, that does also equal the area. However, the total signed area does not necessarily always equal an area that you would think of in the normal sense. Okay? If it's completely positive like this, like if all of your y values are above the axis here, and you're just sitting there adding up all these y values, well, sure, that's going to just be a normal area like what you're thinking of, okay? But this summation is blind, and all it's doing is adding up these function values over and over and over again times whatever delta x you have. In the case of the limiting process, the delta x is the width of a point, and you're adding up the actual y values only, okay? But if you have a combination of positively signed and negatively signed areas, okay, then what that means is some of the y values you're adding are positive, and some of the y values that you're adding are negative. And just like in any other case, if you add positive numbers with negative numbers, they subtract from each other instead of add, right? Instead of summing, they actually make a difference with each other. So if you just blindly add all of the y values together without taking into consideration whether some might be positive and some might be negative, well, then you're not going to get what you would traditionally call an area, okay? This process right here is more than just an area finder. That is a lot of what we use it for, especially when it's in this case right here. But we need to look at it for what it is, a blind adding machine. That's what this is. It's going to sum up all of these function values. And then these are just the symbols right here that we use to symbolize what we're doing. This integral symbol here is actually originally an S. A long time ago it was an S, and it just started getting stretched higher and higher to fit into the mathematical symbols the way it does with all of the things that we do with it, right? It used to be an S though for sum, right? We're going to sum up these things just like sigma and S go together, okay? So this integral symbol is akin, it's the same idea as this, okay? The integral symbol for the definite integral with the numbers is synonymous with summing over an infinite number of rectangles-ish. As your rectangles go to infinity, I should say. You gotta watch the language on infinity there, okay? And what it equals is the total signed area between the x-axis and the function. So in other words, what does that really mean? I'm adding up all the y values, right? The y value is the height between the x-axis and the curve, and this device right here will just simply add up all of those y values, positive and negative, whatever, okay? So you will get a total sum. If all of the y values are the same type, then you can say that your definite integral is equal to an area, okay? If you figure out where these intersections occur on the axis here and here, then you can also guarantee that you'll get little pockets of area, okay? But knowing that this can happen and then taking precautions beforehand can help you do exactly what it is that you're trying to do. Are you trying to just add up all the y values, or are you trying to calculate area? Sometimes those can be different. Maybe my definite integral here isn't about area. Maybe I'm trying to add up a bunch of function values that all represent something like energy or something like that, or temperature, or whatever. I want to add up all of those energy values. I want to add up all those temperature values. Well, then it would make sense to just add all of them, positive and negative. Or maybe these are values that I want to average, right? Positive and negative, and maybe it's some statistical thing. Then it would make sense to just add all of these together and get a total signed area, not necessarily equal to the area. It would just be some total value. But if you're trying to do something like calculate the area, then you're not going to be able to just do the definite integral or the sum from A to B blindly, okay? Adding up all of these would not give me an area value. It would give me a total of all of the positive and negative numbers, okay? So if you run into a problem where it says find the total area, then you need to look for places where these things will intersect and turn from positive to negative, possibly, okay? Separated into sections. And you can do that with summations. Remember, you can actually take a sum from one point to another and add it to the same ending point to another endpoint, right? Split it into two different sums. We can do that with definite integrals as well. These limiting numbers, these boundary numbers, can be broken up into separate sections, okay? Here's a couple of examples. Look, if I take the function negative square root of 9 minus x squared, this is the bottom half semicircle of the circle with the equation x squared plus y squared equals 9. Right? That's the equation of a circle centered at the origin with radius 3. But when you turn it into a function, you have to solve for y, and when you square root, you have to choose plus or minus. In this case, I've chosen the minus to make a point that if I do the definite integral, in other words, if I set this up with my limit and the summation and the function, that would be a really hefty limit and summation to try and resolve, because that is a crazy power with a crazy inside. Luckily for me, I already know that since this is a semicircle, the area is going to be pi r squared over 2, where my radius is 3. So I can skip over all of the fancy limit and summation parts and say, oh, well, look, the definite integral from negative 3 to 3, in other words, adding up all of these y values of this function, is going to be equal to negative 9 over 2 pi. Well, because I knew the radius was 3, and 3 squared is 9. But where did that negative come from? I knew for a fact that this was completely below the x-axis. All of it is, right? From this point to this point, it's all below the x-axis. So every single y value is negative. Every single bit of this is what we would call a negatively signed area, okay? But I am still calculating the size as an area. So I use the formula for the area, but it's a negative because all of my y values are negative. Okay? Next, here's another example where you can have two different sections. The simple line, excuse me, y equals 4 minus x. Y equals 4 minus x goes through 4 on the y-axis and has a slope of negative 1. Hits the x-axis at 4. So if I want to look at all of the values of x from 0 to 10, I'm going to get two differently signed regions. I've got the region from 0 to 4, that's above the axis because I knew the intercept is at 4, right? If I set this equal to 0, I can get x equals 4. So I know that that's the place where all of my y values change from positive to negative because that's where my intercept is, right? We can calculate that. So if I'm looking at the total from 0 to 10, that would be the integral from 0 to 10, right, of g of x. And then I'm just using some triangle formulas here. Again, this is something that I could put into our limiting process like we did before, right? I could plug it in and we can do the limit process, and we'll do an example with that again in this section. But the other part of this section is to look at the shape of what you have. If it's something that you have a formula for, a triangle, a semicircle, a circle, then don't, put yourself through the extra punishment of the limit and summation process, right? I already know the area of some triangle, and then I just need to use my mathematical sense of, is this a positive area or is this a negative area, okay? So right here at the split at the 4, I knew the height was 4, and I knew the width was 4. Area of a triangle is 1/2 base times height. So that's 1/2 of 16, which is 8. 8 is this total area here. And then again, from 4 to 10 is a distance of 6. And it hits this point down here at 10, negative 6. Because if I plug in 10 for the x, notice 4 minus 10 is negative 6. So I knew that the distance here was 6, and it drops by 6 right here. So the area is 1/2 6 times 6. I threw the negative in there just to be cute. The reason that this area is negative is not really because of that, though. Technically, it's still a distance of 6, right? But the area is a signed value because all of these y values are negative. Okay? So this area size is 18, but it's below the axis. So I've assigned it a negative 18 signed area. Okay? So independently, if I were to do from 0 to 4, right, we would get 8. And independently, if I go from 4 to 10, I get negative 18. Well, that means that if I were to do the blind adding machine, this, from 0 to 10, I would get a total of negative 10, which has not the size of either area. Okay? But this is what you would call the total signed area. That's what this would be. The total signed area. What if someone asked you for the total area? Well, that would be different. Okay? Here, let me separate this out right here and give you an example of what I mean for this right here. Okay? For over here, the total area is always when you take the absolute value of everything. So it would be the absolute value of the integral from 0 to 4 plus the absolute value of the integral from 4 to 10. And really what you're saying is that I'm just going to take the absolute value of every different section. I know that I have an intercept at 4, so I'm splitting my sum at 4. And the absolute value of 8 is 8. The absolute value of negative 18 is 18. Okay? So my total area is going to be 26. That's a completely different question than the total signed area. Okay? The total signed area is what the integral would blindly add up and give you. Just if I do all of the adding from 0 to 10, we would get negative 10 because that's all of these y values just added up. But if you're actually looking for a true area, hey, here's this shape. Look at this double triangle shape. I wonder what the area of that is, right? Well, maybe we want to put some tiles down or something like that. that would be the total area, where you have to separate it into positive and negative sections and make sure that you're only taking the size of each one, the absolute value of each one, and then you will get a total size of area. Okay? So that's different than just blindly adding with one of these integrals. Okay? You have to separate it into sections if you want total area. Now you might be lucky. You might get lucky and just have something that's all one type, and then you can just say, oh, look, it's the area. But a lot of times, not so. We're going to have things that dip below and above the x-axis, and you have to know where that happens. You have to be able to find x-intercepts. You have to be able to split it into different regions. Okay? So you can take something that's written like this, and that's really what we're doing with these symbols right now. I'm using this as some symbol to designate, hey, this is the action that we're doing. I'm adding up all of the values of this function from x equals a to x equals b. And don't forget that even though you're going from x equals 0 to x equals 10, doesn't mean that you can't split it up into different sections, x equals 0 to 4, x equals 4 to 10, and try to make different signed regions. Okay? So let's get some more examples of this now that we've got the basic idea out there. Here's some good visuals for you. The function f, y equals negative square root of 9 minus x squared. The bottom half semicircle of the circle that's centered at 0 with a radius of 3. Notice the integral I've put of that function from negative 3 to 3 is indeed this region in between the x-axis and the curve, and it does equal negative 14.14, which is 4.5 times pi. Next, I've got the function g of x is 4 minus x, and it's just this line, right? Goes through the 4 and the 4 on the x and y axes. And then I've got the integrals set up here from 0 to 4. And then from 4 to 10. Right? So I've got a positively signed region this time and a negatively signed region, so that if I actually do both of them put together, you can see the integral from 0 to 10 does in fact come out to be the negative 10 for the whole thing. Since I'm defining the definite integral this way, I want to just practice a couple of conversions back and forth between the limited sum and the definite integral terminology. Okay, so we've got that same definition, the definite integral of a function from some starting point to some ending point is equal to the limit as n goes to infinity, summing all of the numbers I counting from 1 to that n, and x is going to be related to I by having a counting scheme for the x's, and then delta x being of course the width of the rectangles that we're actually adding the areas of, but that delta x being based on a division by n should be becoming infinitesimal, and the limit of course should be the adding up of the function values, really and truly is what this ends up being. Okay, so convert to a definite integral structure, these particular limiting sums here. Okay, so the first way here that you might be presented something like this is just in a sort of generic form here, and the idea being that you're just supposed to see this and recognize, oh, it's a limit of a sum as n goes to infinity, and I have some function times delta x. So right away they're wanting you to just recognize that it's some definite integral of that function. So I'd have fifth root 7 minus 3x, and then delta x just is dx instead when you're doing a definite integral. That's what happens when you let n go to infinity. The delta x becomes infinitesimal and becomes a differential, just like what we talked about with derivatives. Okay, so now the only thing missing is I need the boundaries on my definite integral there. And of course, those have just been handed to me in the 2 to 8. So I would just put 2 to 8 in my definite integral there. All right. Now, the other one down here is, what if they're actually handing you a true limit of a sum, in that it's ready to rock and roll and be calculated, but you want to reverse it and convert it back into a definite integral. Okay, so you need to recognize a few of the pieces. First of all, the times 5 over n should be waving that big flag saying, hey, by the way, I'm delta x, right? And b minus a, whatever they are, happens to be 5. So 5 just is the width of the integral, right? 5 divided by n. 5 is the b minus a. And the fact that it's over n, right, that screams that this is my delta x right here. So this is my delta x. All right. So I know I've got an definite integral, and I can see my function here. Look really closely. See this 6 plus 5i over n? That's our x sub I, right? It's a plus I times delta x. Look, there's delta x, 5 over n right there. And it's 6 plus I times delta x. So this is really just my x sub I, or my x variable. So my function is the negative 35 over 4 plus x squared, right? Negative 35, 4 plus x squared. Okay, so then why do I need the rest of this? Well, I still didn't get my limits, right? Don't forget your delta x gives you dx. I still don't have my boundary limits here, right? Well, look, the 6 right here is my a value. The 6 is the beginning value, right? So it's from 6 to what? Well, delta x right here has a difference of 5. So this must be to 6 plus 5, 11. Okay, double check. 11 minus 6, right? B minus a is 5 over n. And 6 is the starting point plus delta x times I. So this is the definite integral that results from this limiting summation. All right, so now the other way around. And let's actually go ahead and compute it just like we did in the last lecture when we were talking about areas. I have this definite integral. I want to convert it into the limit sum format, and I actually also want to work it out. So in other words, I would like to know what value this sum is. Okay, so let's start by converting it. This is going to be equal to limit as n goes to infinity, summation I equals 1 to n. And I've got my function, right? I've got to put my function with the xi in there. So I'll put a bracket 4 minus something squared, because that's where my xi is going to go. That's where my x variable is. And then times delta x times delta x. Okay? So just keep in mind that what I'm putting here is my x sub I, and what I'm putting here is my delta x, right? I'm trying to follow the format here. So delta x is b minus a over n. So that's 4 minus 0 over n, or 4 over n, right? Okay, now x sub I is always the beginning number plus I times delta x. Well, my beginning number is 0 plus I times delta x. Delta x is 4 over n. So that would be 4I over n. All right. Well, now my limit is set up and ready to go. I'm just going to go ahead and work it out and see if we can get the answer to this definite integral, right? So let's simplify. I've got my limit as n goes to infinity. Remember, the 4 over n is a constant because it doesn't have any i's in it, so I can actually multiply it in the front. It's the same idea as greatest common factoring out of a sum of things, right? Because remember, this sigma means I'm adding up a list of things, and they all have the 4 over n multiplied. So I'm basically factoring out the 4 over n. I is still going to be from 1 to n. And I've got 4 minus, and look, we don't even have to multiply it out this time because it's 0 plus. That's really just 4I over n all squared. So what I have is 4 minus 16 over n squared times I squared, like that, right? So all I had to do in that one, I mean, if this was a number other than 0, right, we'd have to FOIL it out or something. But in this case, didn't need to. I can just simplify the squared like that. All right. Well, now I can take my sum over this subtraction and split it into multiple sums and make it easy to use the old sigma formulas. So I've got limit as n goes to infinity. I've got the 4 over n, and times I've got the summation I equals 1 to n of 4 minus, now remember, this one's going to be the sum I equals 1 to n of the I squared. The I squared is the only thing that's connected to the summation. The 16 over n squared is a constant. That's another one that I can just factor out, but just for that summation. I couldn't factor it out before because the 16 over n squared isn't attached to the whole thing. But when you split the summation, I can factor it out on just that one. Okay, so let's write out the formula for each of these. I have the limit as n goes to infinity. I've got 4 over n times, this is a constant, so I do n minus 1 plus 1. I'm just going to get 4 times n here because of the 4, and then n minus 1 plus 1 is just n. Minus 16 over n squared times, and then you have a formula for the sum of the I squares. That's the n plus 1, 2n plus 1, all over 6, like that. And then, of course, we can do some reduction here. I can take out the squared, because there's 2 n's there, with this n here. I can reduce the 6 and the 16. This becomes a 3, and this becomes an 8. All right. So I have limit as n goes to infinity. I have 4 over n times 4n minus, I have 8 over 3n here, times, and I'm just going to multiply this out, 2n squared plus 3n plus 1, like this. Okay, so one final push, and I'm going to do a bunch of distributive properties here. I got 4 over n times 4n, so I've got the limit as n goes to infinity of 16 minus, now notice when I multiply the 4 over n times the 8 over 3n, that's going to be 32 over 3n squared, and I'm going to take that and distribute it into each of these pieces, right? Okay, so I'm getting 64 n squared over 3n squared, right? So that ends up just giving me 64 over 3. Because 32 times the 2n squared, right? And then 3n squared times 1, basically. So I have n squared over n squared there. That's nice. Next, I'll have 32, and then the 3n on top reduces with the 3n on bottom. So I've got 32 over n for the next one. Because one of the n's is left behind in the bottom. This is an n squared in the bottom. And then anything times 1, right? 32 over 3n squared. All right. Now we go ahead and let the hounds loose on the limit, and he just tears through and hunts down anything he can. Of course, there's no n's on either of these, so they're still there. But this one's going to go to 0, and this one's going to go to 0, because you're letting n go to infinity, and you have an n in your denominator there. So I'm left with 16 minus 64 thirds, which is 48 thirds minus 64 thirds. I'm just getting a common denominator there, and 16 times 3 is 48. So let's see, that's going to be 2 plus 14. That's a negative 16 thirds. Negative 16 thirds is our answer. So it should make you wonder a little bit, how did we get a negative answer, right? The actual answer to this to this definite integral is negative 16 over 3. So how did we end up with a negative number if we're supposed to be adding up areas? And it goes back to what we were just saying in the previous scene of this lecture, okay? Just because I'm doing a definite integral doesn't mean I'm necessarily going to get an answer that is a pure area. We started off talking about areas because originally when we set up this summation, we were doing just positive y values. But let's take another look at 4 minus x squared. That's a parabola facing downward that's been shifted 4 up, right? So that's going to look kind of like this. But then I'm going to be doing from 0 out to 4 when the x-intercept of this is going to be 2, right? Because 4 minus 2 squared is 0. So I have an x-intercept at 2. And notice this parabola keeps sinking down beneath the axis here all the way up to 4. So I've got some positive region here, but I've also got some negative region up to the 4 there. And in fact, since our answer is negative, that means that the negative region was larger than the positive region, right? Because positive plus a negative, it's whichever one's larger is the leftover. So that's how you convert between the two formats of definite integral and limited summation. Being able to go back and forth is something that we need to be able to do. And obviously on certain definite integrals, they're pretty straightforward to compute. Here's a better drawing of that integral that we just computed using the limit summation. The function 4 minus x squared here, and I've even broken it up. Here's the whole integral that we just computed. Negative 16 thirds is the total. That's the negative 5-point continuous 3. But notice the reason for that is because we have a positively signed region and a negatively signed region. 5.33 and then negative 10.6666. That's a continuous 6 there. So actually the negative region is exactly double the positive region there, and that's how we end up with the negative total of negative 5.3 here. That's the total for the whole thing. Let's deepen our understanding of the connection between the definite integral, the limited sum, and the areas that are trapped between the x-axis and the function's graph. Let's start with something straightforward, like if you're given one region, can you extrapolate to more? Okay, so we all know sine x, the sinusoid wave here, has a high of 1, has a low of 1, and it's a very symmetric shape. The hump here is the same size and shape as the trough here. And even with the cosine function, those two functions are the same shape and everything. This is a nice, completely symmetric shape. Okay? And later on, when we have more calculus theorems, I'll even prove this to you. But for now, let's just go on our visual symmetry. Okay? If you're given that the definite integral from 0 to pi over 2 of sine x is equal to 1, then extrapolate that into these other two definite integrals, okay? Or summing with limits, if you will, or finding areas between curves and signed areas. It's important to notice that too. So on the graph here, I've even shown you, from 0 to pi over 2 is the first half of the top hill of a sine curve, okay? And so what we're saying is that the sum of all the y values there, or the area between the curve and the x-axis from 0 to pi over 2, is equal to 1. Kind of cool, right? The fact that it peaks out at 1 and it's already added up all of the y values to get 1 up into that point, right? Okay, well, then what if I wanted to go from 0 to pi? And don't forget, pi is right here in the middle where it hits the x-axis again. Well, it should make sense to you that I've got two of these symmetric pieces here. And so this particular definite integral should be 1 plus 1, which is 2. Okay? Then what about 0 to 2 pi? Well, I've got the same shape, but down in the negative side, it's below the x-axis. Each one of these should also be a size of 1. So would it be 1 plus 1 plus 1 plus 1 and give me 4? Be careful. The area size here is 1, here, here, and here. But don't forget, this is beneath the x-axis. So technically this is a signed area region. These are both going to be negative 1s. So what we're getting from 0 to 2 pi, starting at 0 here, going all the way across to 2 pi, is going to be 1, 1, negative 1, negative 1. Like this. So it's actually equal to 0. Now, if the question were rephrased, what is the total area trapped between the curve and the x-axis? Total area would be 4, because you would knock the negatives off if it's just area. Okay? But remember, definite integrals and limited sums are blind adding machines. They're just going to add the y values that are presented in order. So it would simply add all of these up and get that 0 sum if you just go straight from 0 to 2 pi. If you summed from pi to 2 pi, you would get a straight negative 2. If you summed from pi over 2 to 3 pi over 2, you'd get 1 and negative 1, you'd still get 0. So be careful where things go through the x-axis, as we've been saying. Now, here's another example where we're going to do all of this without doing limits and sums. Again, I'm just going to use formulas that we know from geometry in order to find what these definite integrals are. So let's start with computing the definite integral from 0 to 4 here. Well, here's 0 and here's 4. So they're talking about finding the area of this region here. This region right here. But that's not a normal looking shape. It's not even a good looking triangle here on this guy. So I'm not going to do it that way. Instead, I'm just going to break it up into some shapes that would be more familiar. Right here, I'm going to split it down the height right here. And that's going to give me a right triangle on this side over here. So the area here of this piece, I can compute as 1/2. The height right here is 3, because it goes through that point where the height is 3, see? And then the width of the base is 2. So then this whole area right here, I'm getting a positive 3. Okay, then I'm also going to split right here so that I can get another triangle up top and a rectangle down on the bottom. The area of this rectangle right here is just length times width, right? The width is 2, the length is 1. So I'm getting a positive 2 here. And then up top right here, I've got a width of 2. And what's this height? It goes from 1 to 3 right here. It's a height of 2 also, right? So the area of this region right here is a triangle, 1/2 base times height. 1/2 of 2 times 2, right? So I'm getting another +2. Now, the total add up, right? They're nothing but positive values. So I can compute the definite integral from 0 to 4 by just adding those up, right? That's 4 plus 3. This total should be 7. Next, from 4 to 9. Why was it important to split at 4, do you think? We went 0 to 4, and now we're going 4 to 9. Well, look, at 4, what happens? It goes negative, right? So over in this region right here, I'm going to be adding up something that's totally negative. I'm separating this region from the other region so that I don't intermix any negative and positive values. So there's a couple of ways that you can go about doing this. One way is you can split it here and here, and you'd simply have a rectangle and 2 triangles. The triangles are 1/2, 1 times 1, right? Because it goes through -1 here. So this height right here is 1. So this would just be a 1/2 size. And so with this, it's 1 by 1. And 1/2, 1 times 1 is, again, 1/2. But we got to be careful here. This is actually a -1/2, right? And so is this one. This is going to be a -1/2 as far as the signed area goes. Okay? And then what about this region in here? It's a rectangle, has a width of from 5 to 8, so a width of 3 and a height of 1. So 3 times 1 is a -3 sized area. Okay? For a total, -1/2 is -1, and -3 should give me a total signed area of -4 when I'm going from 4 to 9. The other way, by the way, is you could have noticed that this was a trapezoid, and you can take the area of a trapezoid by doing the height times the average of the 2 bases. The 2 bases are 4 to 9, which is 5, and from 5 to 8, which is 3, and the height is 1. So it would be 1 times the average of 5 and 3, which is 1 times 4, right? So you get the -4 either way. Okay, so you can use your trapezoid there as well. And then I have another positive region here. That's why we split here again, right? I have another positive region right here. I'm getting a positive 1/2 again because it's 1 by 1 and it's a triangle, 1/2 base times height. So I'll put a 1/2 here. Okay, so now let's answer the 2 big questions. Compute the definite integral from 0 to 10, which is considered the total signed area. In other words, I'm just adding up all of the y values from beginning to end, blindly just adding them. So that would be 7 minus 4 plus 1/2, right? We would get 3.5. Or if you want to do 7 over 2, that's fine too. Okay? because I'm just adding them all up. But if the question says what is the total area trapped between the function and the x-axis, okay, that would be 7 plus the absolute value of negative, well, technically they would all be in absolute values, right? What you do is you take the absolute value of everything, just, okay, all the different sections, absolute value. We would get 7 plus 4 plus a half, which would give me 11.5. Okay? So you need to know the difference between just the blind adding total signed area and what is the area trapped between the curve and the x-axis. Some other important properties that carry over from the limit sum over to the definite integral. Since we are equating these two, since you can see that a definite integral is being created from a limit of a summation, then a lot of those properties of summations just carry right on over. And then there's one more property in there that you wouldn't think of until you actually see it. And let's talk about these three things. So look, from the standpoint that these were made from summations, the top property here and the bottom one should make total sense, right? If I have a multiplied number times the thing that I'm adding up over and over again, I can simply bring that multiplied number outside of the summation, or in this case, the integral, and then multiply it after I'm done getting the total integral. And if I'm adding up a list from A to B of function values, and then I'm also adding up a list from B to C, and this is of course given that B is in between A and C, although you can actually prove that it doesn't totally need to be. But let's say I have, some intervals like this, right? And one integral is from A to B, the other integral is from B to C. Of course, if you add those two, it would be like adding all from beginning to end, from A to C. And then there's this other property here. The fact that the integral is a directional sum. That's what this really is. Integrals are directional sums. So it matters which way I list the beginning and ending numbers. The integral from A to B is actually the opposite, the negative of the integral from B to A. Typically, we read our x-axis from left to right. We go this way when we read, and we're adding up the y values in that way. If you were to attempt to start at 1 and then go the other way, you have to see it inside of the sum. It would affect the way that your x sub i's are being counted. You would actually count the first xi on the opposite end, and then you would be subtracting xi, delta x's at every rectangle. Okay? So the way that integrals work is that you actually have a directed sum. Usually they would increase with the normal positive x-axis. But if you reverse your direction, then you can just get the opposite, but it's the same total sum. Here's some examples. If you are given, or maybe at some point you were already calculating, that the integral from 9 to 5 of some function h of x is -4, and the integral from 7 to 9 of h of x happens to be -13. We want you to compute the integral from 5 to 7 of 6 times h of x dx. So let's set up a couple of things. First, I'm going to notice that 9 to 5 is not the typical way that we would run that. So if I were to take this property right here from the directed sum property, it's going to tell me that the integral from 5 to 9 of h of x dx is actually the opposite of this, which would just be 4. That's what that property is going to tell me there, because I swapped the direction of my boundary limits. Okay, so I'll be adding in the other direction, and I just get the opposite of the area there. Well, not area, the opposite of the signed area. And then from 7 to 9, I've got negative 13. Well, this is from 5 to 9. Well, what I can say is that the integral from 5 to 9 of h of x dx would definitely be equal to the integral from 5 to 7 of h of x plus the integral from 7 to 9 of h of x. According to this rule right here, right? The fact that if I want to add up everything from 5 to 9, I could do it by adding everything from 5 to 7, and then adding everything from 7 to 9, and then combining those later. Sure. Well, I already know what the sum from 7 to 9 and the sum from 5 to 9 are. This one is 4. Integral from 5 to 7 h of x dx plus the integral from 7 to 9 of this function is negative 13. So if I just add 13 to both sides here, I will get that 17 is the definite integral from 5 to 7 of the function h of x dx. So 17 is the integral of just h of x. This calculation right here is 6 times that, and remember, I can take any multiplied constant and just multiply it after. So for my final answer here, I can say that this is just going to be 6 times the 17, because this is from 5 to 7, you see. So then times the 17 would give me my final answer of 102. Right? 42 and 60, yeah. So just using a few of the properties of definite integrals that carry over from the way we've defined it, right? The fact that you can split it along different boundary limits, and if you reverse the limits, you get the negative answer, the opposite of the answer, and the fact that if you multiply a constant, it can pass in and out of the integral symbol. Okay, now we're going to switch gears slightly to an application using definite integrals. We're going to expand the mean value theorem into the region of integrals. So we have the integral version of the mean value theorem. It's still the mean value theorem, okay? But it works off of areas this time instead of slopes. What you have to imagine is that you have some function, okay, f of x, and you're interested in it in some region between x equals a and x equals b. So I'm really just interested in this piece right here. If you find, and remember we're on a closed interval, right? It's continuous, f is, on a closed interval, just like the old version of the mean value theorem. And that means that the function must take on a maximum and minimum values because of the extreme value theorem, right? So let's say you know where that maximum is, and we'll call the y value, that is the maximum, capital M. And let's say you know where the minimum value is, we'll call it little m, that's the y value of it. And of course those are both happening somewhere between a and b. So if you know what those values are, if I were to look at the rectangle that has a height of that y value, capital M, and of course it would have the width of the interval, b minus a. And also if you were to look at the rectangle with height little m, same width, b minus a, then the area of the integral, right, the area that's formed by adding up all the y values from the integral, would have to be something in between the area of the small rectangle using the minimum and the large rectangle using the maximum. Okay, so this area that we're talking about with the integral would have to be somewhere in between b minus a times m and b minus a times big M. The value of the integral has to be in between those. We can call that, a lot of people like to call that the comparison theorem. You can actually figure out if it's an integral that's too difficult to do by hand, you can actually figure out some limitations of what this value of the integral has to be. But put another twist on it, if I divide by b minus a in all three places, then I'm just left with little m and big M on either side of the inequalities. And then I have 1 divided by b minus a times the integral of f of x dx. And what we do is we define this quantity right here. Think about it for a second. I'm adding up. Remember, the definite integral is a large sum of just a bunch of function values. I'm adding up all those function values. But then I'm also dividing by the length of the interval. That's how many y values I have, in a way, right? So I'm really averaging this. We define the average function value to be 1 over the length of the interval times the definite integral of the function on that interval. Okay? And we usually only use continuous functions to do this with, and the continuous functions are the ones that work with the mean value portion of it. If f is continuous on that interval from a to b, then what this is saying is that the mean value theorem is guaranteeing that there will be an average value somewhere in between the lowest function value and the highest function value on the interval. Basically, it's guaranteeing that the function will take on the average value somewhere in between. Because as we said, f of x is going to be continuous if the mean value theorem is going to work. So the mean value theorem is going to say somewhere in between the lowest function value and the highest function value will be the average value. And since f is continuous, it will take on all of the values in between little m and big M. So there must be at least one point, one x value, where f of that x value is equal to the average value. Okay, so that's what the mean value theorem is guaranteeing here, that there will be at least one value between a and b where the function takes on the average. Okay, and as you can see, the average between big M and little m, depending on how the function is weighted, the average is going to be somewhere here-ish, right? Let's say this is the average value here. As you can see, the function does in fact take on that value, right? I'll call it c for a moment. Okay, where f of c is equal to this average value. So just like the old mean value theorem, it guaranteed somewhere in there where the derivative would be equal to the average slope. Here, we're saying that the average function value must be one of your function values between a and b, and it has to be, somewhere between the very maximum and the very minimum of your function. Of course, it's an average value. Okay, so first example, find the average value of a function. Just that's a particularly good use of this formula right here. Just the fact that we can find the average function value is important. Good use in statistics even. We have to be able to find the mean of a distribution, and if it's continuous, this is the way to do it. I'm going to find a way to sum up all of the function values, and then I'm going to divide by the length of the interval. Okay, so my interval is from 1 to 5 here, as you can see, 1, 5, right? And we have our function r of x is 3 plus the square root of 4 minus x minus 3 quantity squared. Okay, so if you pay attention real close, then what you should be seeing is that this is just a rewrite of the circle x minus 3 squared plus y minus 3 squared equals 4, which is the circle centered at 3, 3 with a radius of 2, right? But since I'm only using the positive square root here, it's just the top half, and that's what makes it a function. Okay, So the average value of this, I would compute like this. The average value is 1 over b minus a, that's 5 minus 1, times the definite integral from 1 to 5 of our function r of x. Right? I don't feel like having to write out the whole radical, but you can put the radical there if you want. I'm just going to use the function name instead, since we're not actually doing anything. Obviously, I'm not going to put this in a limit of sums. That would be a nightmare with this particular function. But I do know that it's a circle on top of a rectangle, right? So I can compute these areas here very quickly and easily. The top half region up here, right? That area has to equal 1/2 pi times the radius squared. So 1/2 pi times 2 squared is going to be equal to 2 pi. And this region down here is a rectangle, right? Length times width. This area right here is just going to be 3 is the height, right? That's the shift. And then 5 minus 1 is 4. 3 times 4, 12 is the area here. Okay, so then the total definite integral from 1 to 5 of the function is all of these y values being added up from the axis up to the curve. So I have the area 12 and the area 2 pi there being added up together. So let's simplify here. This is going to be 1 over 4 times, right, times the value of this definite integral, which is 12 plus 2 pi. So then what does that end up being? 4.57. Ish. So 4.57 is the average value, right? 1, 2, 3, 4.5. The average value is here. Well, ish. I didn't get it quite halfway, did I? It should be about right there, actually. Sorry about that. Ish. Not drawn to scale, right? But close enough. As you can see, there are 2 points this time that take on that average value there. The mean value theorem just guarantees at least one if you have the continuous function there. So I want to finish up with one more example with average value of a function here. And let's actually do what the mean value theorem guarantees. And that is, if your function is continuous on some closed interval, that you will find a value, an x value somewhere in the interval that takes on the average value of your function. Okay, so let's talk about it. Where does this function 4 minus x squared equal its average value on the interval 0 to 4? Well, I think we're kind of in luck, right? Earlier in this lecture, we already did some of this computation. So right here, first of all, we need to find the average value, right? The average value is going to be 1 over 4 minus 0 times the integral from 0 to 4 of our function 4 minus x squared dx. Okay, so that's going to be 1/4 times, now we did this integral earlier, right? We did this integral using our limit of summation, and we found it to be -16/3. 1/4 times -16/3 is equal to -4/3. So my average value of this function on this interval, right? Let's draw this out now. The interval is from 0 to 4, right? So here's 4 right here. Goes pretty far down. and it starts at 0 here. So from 0 to 4, this region right here, we're averaging it out to be negative 4/3, which is just negative 1 1/3 ish. So it should be right here. This point right here should be somewhere in here that our function takes on. Notice it does actually hit, right? We should be able to find an x value somewhere in here where the function is actually equaling that average value. Okay, so let's compute where that is. I'll just set negative 4/3 equal to my function. Right? Now that I've found the average value, I simply just set it equal to the function to see, hey, where does this end up landing? Okay, so I'll add x squared and I'll add 4/3. Like so. 4 is 12/3, so I'm getting x squared is equal to 16/3 total. And then I'll take the square root, and I'm getting x is plus or minus 4 divided by the square root of 3. 4 divided by square root of 3 is 2.3. So approximately plus and minus 2.3, right? As you can see, it does actually hit on both sides, right? Because it would hit over here as well. And 2 and some change, right? 2.3 is right about where we have that point listing out right there. So maybe I did graph it pretty close to the way it's supposed to be, right? Okay, so obviously I'm not going to take the negative because that's not in my interval, right? But in the interval from 0 to 4, right, I can say that f of 2.3 ish, the average function value. So when it says where, right, this is what we're talking about, where x is approximately equal to 2.3. So I hope this lecture has helped you see the connection between the definite integral, the y values between a graph and the x-axis, and the positive and negative signed areas can be, along with finding the average value of a function.